In this recording, we're going to look at something called the ambiguous case. If you remember from geometry, if you have side-side angle, it doesn't necessarily prove congruence. Remember, if you say it backwards, it spells something bad. So what we're going to do is use the law of sines. We're going to determine how many triangles are possible given these particular sides and angles, this side-side angle combination. And the answers are simply 0, 1, or 2. It's never 3. Okay? So let's look at this particular triangle. Okay? I'm given a side, and an angle that's not between them. So I'm given that side A is 8, side B is 9, and the angle A is 54 degrees. And I'm wondering if there's any other triangles that could be formed given that bit of information. Okay? So let's look at a dynamic representation of this using Geometer Sketchpad. Okay, so according to the given information, I have to keep side A at 8, I have to keep side B at 9, and this angle has to say 54 degrees. Okay? So I'm going to move this point along this line. Notice side B here hasn't changed, the angle A hasn't changed. I need to move this point so I can get this side back to 8. Get as close as I can and make it 8. Again, I have side A still equals 8, side B equals 9, and angle A equals 54 degrees, but I have quite a different triangle. And if you'll notice, this angle here, 114.4 degrees, is the supplementary angle from the angle B that existed before, 65.6 degrees. So what's the point here? Well, the point is, I can create two triangles given this information. And how will I be able to determine that using trigonometry and algebra? That's our task today. Okay, so once more, we have these two triangles side by side that have the given conditions, the 8, the 9, and the 54 degrees. And you'll notice here that the angle B, this angle down here, is 114 degrees, whereas the original angle B was 66 degrees. It's important to notice that they are supplementary angles. We're going to use that fact in our approach today. Okay? So we're going to look at several examples. I'm just going to ask for you to jot them down, and each time the question is how many triangles, how many distinct triangles are possible given these conditions. We're always going to be given a side, and an angle. We're going to go slowly at first, and then you're going to see that it's the same process every time. We're just going to need to set up a law of sines, solve for that unknown angle, and then do an analysis or an interpretation. Okay? So I'd like you to set up a law of sines proportion for side A, side B, and angle B. Okay, so hopefully you set up something like this. Sine A is the angle that's unknown over 10, sine of 20 degrees over 12. We need to solve this proportion. Okay, so we multiply both sides by the LCD, the 10 and the 12. At this point, we divide out the 10, we divide out the 12. And now I multiply what's left. 12 sine A equals 10 sine 20. I want to be able to get angle A by itself, so I'm going to divide both sides by 12. And I'm going to end up with the sine of A, which is here, these 12s divide out, equals 10 sine 20 degrees over 12. Okay? If we're solving for an unknown angle, we need to use inverse trig. So let's get our calculator out, get into degree mode. We're going to use degree mode throughout this unit because we're talking about triangles. Radians are relevant for circles and for graphs. So I'm going to go to my calculator. I'm going to do the inverse sines. I want to get rid of the sine function of this ratio here. I'll model for that one time on this video. Okay, so in our calculator, we check our mode. It's got to be in degree mode. Then we're going to go inverse sine of the fraction 10 times the sine of 20 degrees all over 12. Close the parenthesis. And there's our angle A. We can approximate this to be 17 degrees. We're not going to need to be more precise than that. Okay, so now we know that angle A is 17 degrees. Here's where we need to do the analysis. Before it was just plugging in some numbers to our formula. Okay, so I'm going to concentrate for a moment. If there is another triangle, what would be the possible other value of angle A? And if you remember from our demonstration, if there is a second angle, that angle is supplementary. Remember, 66 and 114 were supplementary. So if there is another angle A, it's going to have to be the supplementary angle of 17. Okay? It'd be 163 degrees. I want to show you how that works on the calculator, so please grab your calculator. Okay, we're going to type in the sine of 17. And we're going to type in the sine of its supplementary angle, 163. Notice how they're exactly the same? And that makes sense because remember, all students take calculus. 17 degrees in quadrant 1, 160 degrees in quadrant 2 have the same reference angle. So therefore, they're both positive in quadrants 1 and 2. The sine is positive. So the question is, well, which one's right? Is it supposed to be 17 or is it 163? They're both right. They both just might not be correct in this particular context. So let's look at our example again. Okay, this is where I need you to really concentrate. We said 163 has the same sign as 17. Which one's right? Maybe one, maybe both. However, if we put a 163 degree angle in a triangle that already has a 20 degree angle that can't change, that's too many degrees, right? That exceeds 180 degrees. Therefore, we cannot have a 163 degree angle. The only triangle that works is the one triangle we originally got with the 17 degrees. So there's only one triangle. Let's look at another example. Okay, be patient with this. It's going to get easier. Okay, in our second example, I'd like you to set up a law of sines proportion and get as far as you can and then play the recording. Okay, we're trying to solve for the unknown angle, angle B. Okay, so hopefully you set up sine 35 over 2 equals sine B over 5. We're going to multiply both sides by 5 and 2. And now we've got that sine of B is equal to 5 sine 35 degrees over 2. We want to use the inverse sign, solve for angle B. Go to our calculator, we do inverse sine of this number, but we get an error because we can't take the sine of a number that's bigger than 1. If you remember from your graph of sine, it never got above 1. Can't do it. So if you can't have a triangle, we just say it's not possible. There's no triangles that exist given these conditions. Okay, so again, if you reach an error, you didn't make a mistake, it's not possible to have it. Our next example, I'd like you to do the same thing. Set up your law of sines, solve for angle B, then play the recording when you're ready for the analysis. Okay, so hopefully you set up your law of sines like this. It's always the sine of angle A over little a, sine of angle B over little b. Multiply both sides by 7 and 10. Get the sine B on both sides by dividing. Now we're ready to use our inverse sine. Okay? Inverse sine of that ratio does produce an angle. So the question is, what would be the other angle that would have the same sine? Well, it would be its supplementary angle. So if there is a second angle B, it would be 180 minus 59. Okay, if you put that in your calculator, sine of 121, sine of 59, you're going to get the same ratio. Let's see if that's possible. This is where you have to really concentrate. Can we fit a 121 degrees angle in with a 37 degree angle? And yes, we can. 37 plus 121 fits nicely. It's under 180, so therefore there are two triangles that could possibly exist. One with a 59-degree angle, one with a 121-degree angle, and just like the one we looked at before that had two triangles, both the angle B's in this case were supplementary. That's the same situation. Okay, so hopefully this is getting a little easier for you, setting up your law of sines each time. I want you to set up your law of sines proportion for this one, then play the recording when you're ready to do the analysis. Okay, so hopefully you set up sine of A over 10, sine of 30 over 5. Multiply both sides by 5, and then 10. Do the inverse, and we're going to end up with A is equal to 90 degrees. And this is a sort of special case, so really concentrate on this one. Obviously, if the supplementary angle of A is 90 degrees, there's not going to be another distinct triangle. Okay, there are, I guess, two triangles, but they're the same exact triangle. They're congruent. So we say is there's one right triangle that exists, okay, because the supplementary angle is congruent. So there's really only one distinct triangle that could possibly exist with a right triangle. Okay. Our last two examples are going to involve obtuse angles. Okay, and with an obtuse angle, there can only be 0 or 1 triangle. Okay, because I can't have two obtuse angles in the same triangle. It just wouldn't make sense. We're going to use that same approach. We're going to set up our law of sines. So set up your law of sines, please, then play the recording when you've got that figured out. Okay, so hopefully you set up your law of sines. You worked out, you found that sine of A is equal to this ratio. Okay, let's figure out what angle A is. Okay, so therefore angle A is equal to 64 degrees when you do your inverse sine. Now you have to do some analysis here. Can we have a triangle that has 64 degrees and 135 degrees? Okay, hopefully you recognize that, wait a second, that's too much. That would not fit in 180. So because 64 degrees plus 135 degrees is too big, it's bigger than 180, no triangles exist. Remember, our choices here are either 0 or 1. And in this case, it's 0. So if you're playing along, you're probably guessing that if you gave me an example that's a 0, there's only 0 or 1, this one's probably going to be a 1. And you're right. But let's do the work to just make sure. Okay? I want you to set up your law of sines, figure out your angle B, and then play the recording when we're ready to do the analysis. Okay. So if you've got your law of sines set up like this, sine B over 11, sine 112 degrees over 14. Multiply both sides by the LCD, divide by 14, and now we're ready to use inverse sine. At this point, use our inverse sine and we get that angle B is 47 degrees. Now remember, it's just for an obtuse angle. We started with a 112. It's either it's a one triangle or it's a none. So 47 degrees, our question is, can that work with the 112? And yes, because 112 degrees and 47 degrees is less than 180, it works, it fits. So there is one triangle that exists. Thanks for watching.